We'll be employing the System GMM approach, and for this, we'll closely follow the methodology outlined in the Brown and Peterson Journal of Corporate Finance 2011 study and carefully select variables that are quite similar to theirs. As is my usual practice, I'll be referencing the Finances Research Gate. We should go ahead and select the annual frequency for this data, and then we can begin choosing the primary variables we need. But before we do that, I should probably define the specific time frame. Let's go with the period from the year 2000 through 2024. The idea here is that we are going to model the R&D dynamic, the research and development, and the explanatory variables. They are book to market.
Revenue is growing.
We have the option to select the cash flow category from the menu. And problems concerning our current inventory and product availability.
And finally, the most important explanatory variable that we have considered in this model is the total cash holding. And for our Y variable, we are going to use the R&D intensity, which represents the total research and development. Once we have everything ready and all of our parameters are set, we can go ahead and check it.
The ones that are different from the rest.
However, we also have the capability to, for example, choose specific characteristics such as age or size, especially if your objective is to subsequently divide the regression analysis based on these particular variables. Then, before we can truly proceed with our main analysis, it's always an absolutely essential and necessary step to meticulously check for any potential outliers within our dataset, and that is precisely what we're doing right now. So we must effectively deal with those anomalies. And for this purpose, let me explain that I will be using the technique of Winsorization. I'm going to Winsorize all of the variables, specifically those denoted as X, at
the 1% level of significance.
And then you go and create them.
Once all of our tasks have been fully completed, we will then be able to select that specific option within the advanced regression settings. Let's make sure to select every single one of the items that we have organized.
The appropriate choice here is to select the System GMM. This specific methodology is commonly referred to as the Blundell and Bond approach. In our previous video, we explained the Arellano and Bond estimator. In this video, let's take a completely different approach and let me explain the full meaning behind it. So we have this main equation that we are currently modeling, which is the R&D dynamic. And the lagged R&D also plays a crucial role within the equation, primarily because we're dealing with an autoregressive process. This essentially means that the impact of R&D isn't confined to a single year, rather it unfolds over an extended period, often several years. Therefore, the effects from a previous lag period can indeed be directly linked and influence the R&D outcomes of the subsequent period. Furthermore, we have the explanatory variable in addition to the firm fixed effects and the error terms. Now, in order to successfully remove the firm fixed effect, we must take the first difference of the variables, and we are then left with this resulting equation. And instrumenting this equation has an endogeneity problem because this part is correlated with the error. The fundamental reason for this observation is quite clear. If you consider this specific component, which represents the lagged R&D term subtracted by two previous lags of R&D, and then you also examine the equation that incorporates a single lag of R&D, you will inevitably discover that the lagged error term is inherently included as a crucial element within the structure of this very equation. Therefore, the lagged R&D variable includes the error component, and in this particular instance, we see that X is directly correlated with the error term itself. Whenever you have a situation where an independent variable X is correlated with the error term in your model, that's when we encounter a significant endogeneity problem. To address this, the Arellano-Bond estimation method provides a solution. We typically fix this by instrumenting the problematic variable using distant lagged values of R&D, such as the second or third lags. And that might actually resolve the entire issue because these elements may not be directly connected to any potential future error that could arise. Therefore, they are essentially predetermined in that particular sense, which means we are perfectly able to utilize them.
Now, the system GMM approach will incorporate an additional set of equations. So we will include the difference equation, which constitutes the Arellano and Bond component, but we will also introduce another equation, specifically known as the level equation. For this level equation, we intend to utilize the raw level of R&D data without any differencing applied. This particular equation presents a significant challenge, primarily because the approach of instrumenting variables and levels, especially when incorporating lagged levels, inherently creates a difficulty. This issue arises due to the presence of the firm fixed effect, which complicates the estimation process. So, in order to solve this problem, considering that we also have endogeneity, given that the error here is correlated somehow with the explanatory variable, then we are unable to simply employ the delayed level of R&D, for instance the second-year lag, as we previously did, since that particular lag will possess a firm fixed effect.
Therefore, we are going to utilize the difference as our primary instrument.
So, the difference equation uses the lagged values as an instrument, specifically the lag level of the variable, and then in the level equation, we are going to use the difference as an instrument. This is precisely how the system GMM equation operates. Naturally, there are two primary assumptions that we must consider here. First of all, the lagged level of research and development should not have any correlation with the error term. Furthermore, for this specific model, any given x variable should not be correlated with the firm fixed effect, which implies that the difference of the x variables here must remain entirely independent of those underlying fixed effects within the firm. And this is truly the case because as soon as you apply the differencing technique to your data, you effectively eliminate all of those time invariant and firm-specific characteristics that might be there. So, the underlying concept here is that the system GMM approach can offer greater resilience, particularly when dealing with a pronounced autoregressive component. This means that the lag y variable, as observed in this specific scenario, is exceptionally close to a value of 1. Consequently, in such circumstances, the system GMM methodology gains significantly in its overall importance and relevance. Here, as we had indeed anticipated, we are observing a rather substantial and significant lag. This particular situation explains precisely why the research and development initiatives are both inherently dynamic and quite resistant, and following this, we can examine these specific coefficients. As we had in fact expected, the available cash flow demonstrates itself to be quite significant, primarily due to the fact that this cash flow is absolutely essential to effectively smooth out the various financing constraints that are faced by the firm. So, companies possessing greater cash reserves tend to undertake more research and development. This is because if they encounter any unexpected financial shocks, they can readily use their available cash to smooth over these temporary disruptions that arise from various financing events. Adjusting R&D is a problem because of the adjustment cost, and therefore if there is no cash buffer, then firms will be more reluctant to engage in R&D. So the presence of cash here will solve the issue, and that will encourage more R&D investment. Well, another important thing we need to examine is the Hansen test, and ideally this test should not be significant, because if it turns out to be significant, it would imply that our instruments are correlated with the error term. Additionally, we also need to consider the second-order autocorrelation of the differences in our errors. The first one is normally significant, but the second one shouldn't be significant in order for us to proceed. If it's significant, it means that we need to use more distant instruments. For example, instead of using the second lag of R&D, the difference equation, we might find it necessary to employ perhaps a third or even the fourth lag. This would be done specifically to ensure that we effectively avoid any potential issues with error autocorrelation, especially if it proves to be substantial. However, in our current situation, we fortunately do not encounter this particular problem, primarily because the p-value we observed is not statistically significant. From this point, we can implement a particular configuration and then manage some of the x variables. If you're absolutely certain that some of those specific x variables are not endogenous at all, but are instead truly exogenous, which means that they are not correlated with the error term in any way whatsoever, and they are not influenced or determined by any other variable within the model's equation, then yes, you are definitely able to select them and treat them as exogenous factors in your analysis. This approach will significantly decrease the total count of instruments we need. Previously, we used 25. But now that number has dropped to just 13. This is because we no longer need to create instruments for variables that are considered purely exogenous. Instead, we only apply instrumentation when a variable is either endogenous or predetermined, which depends entirely on its specific characteristics. Furthermore, you have the ability to determine the specific time lag for research and development in this particular scenario. For instance, we typically select a value somewhere between 2 and 3 years. However, you are certainly free to increase that figure if you find it to be necessary for your model. Therefore, you might want to begin with a relatively small number, which is the standard default setting provided here, such as 2 or 3. If it meets our expectations and fully satisfies all the required conditions, then that should certainly suffice. However, if it doesn't, then we might find ourselves needing to significantly increase the number of lags applied to our research and development efforts. To illustrate, should we decide to expand those parameters in these these specific areas, it would naturally lead to a corresponding rise in the total count of instruments required. However, in this specific instance, it's not selected since there's no requirement to add more instruments. Consequently, the system will automatically choose the lowest value and incorporate that into the final table outcome. And that concludes our discussion regarding the GM-GMM system. We appreciate you taking the time to watch this presentation.